A company produces steel rods. The lengths of the steel rods are normally distributed with a mean of 138 centimeters and a standard deviation of 0.9 centimeters. For a shipment, 26 steel rods are bundled together. Find the probability that the average length of a randomly selected bundle of steel rods is between 137.6 centimeters and 138.2. Now let me point out that we are bundling 26 steel rods together and calculating their average length. So the formula we're going to use is a little bit different than if we were just picking one steel rod. Specifically, we are looking at using the Central Limit Theorem. So first of all, I'm going to note that 138, my mean, is right here in the middle. So 137.6 is somewhere over here on the left, and 138.2 is somewhere over here on the right. And I want to find the probability of being between those two numbers. That is, find the area between those two. So the first thing I'm going to do is convert each one to a z-score. So let me make a note of which one I'm converting. This is going to be for the z-score for 137.6, and this will be the z-score for 138.2. Now, normally, this is the z-score formula. But because we're talking about the average, we're not calculating a z-score for an x, we're calculating a z-score for an x bar. But that means the mean and the standard deviation are also for x bar, the mean of those 26 steel rods. So what this formula actually looks like is, well, it turns out the mean of sample means is the population mean. So that actually doesn't change, but the standard deviation for sample means does change. That's going to be the population standard deviation that we're given, but divided by the square root of our sample size. So for us, this looks like 137.6 minus 138, all divided by 0.9, our standard deviation, divided by square root of 26. All right, and that, let me show you how I enter this in the calculator. If you have a scientific calculator like the TI-30X2S, you can follow a similar format. I like to wrap my numerator in parentheses and then divide by, and again, wrap the denominator in parentheses. If you don't, your calculator will think that the square root of 26 is being multiplied to the is being divided by, is dividing into the fraction. So we have a z-score of about, let's call it negative 2.27. All right, I'm following the same formula for 138.2. Same mean, same standard deviation. This comes out to be about 1.13. Now what I'm going to do is look up the probability to the left of 1.13 to get the area to the left of 1.13, and then look up the area to the left of negative 2.27, and subtract off the area to the left of negative 2.27. All right, so I'll do this in two ways. One using the normal distribution table, and one using spreadsheets. So let's start with 1.13. On the table, I'm going to look up 1.13 as a z-score. That is 0.8708. And so that is the area to the left of 1.13. Now let's look up negative 2.27, and we're going to subtract that area off. Negative 2.27 is 0.0116. Okay, and if I subtract those, I get 0.8592. Now on a spreadsheet, one way I can use a spreadsheet is to calculate the area to the left of these z-scores and avoid using the table. So to do that, I just have to say equals norm.s.dist and plug in the z-score. I could do that again for, I did it for 1.13, I can do it again for 2.27 negative. And then I could subtract those. And I'll have a few more decimal places of accuracy, but rounding to 4 decimals is usually good enough. And I again then would get 0.8591, 92 rather. Now let's say I wanted to use a spreadsheet and I wanted to avoid doing the z-score calculation altogether. Well, I can do that by, as opposed to the norm.s.dist, I can use the norm.dist function. The S stands for standard, and that means it's looking for a z-score. The norm.dist will take your x's that you're given, and that's the 137.6 or the 138.2, and it will calculate the z-score for you and do all that in the background. So let's start with 138.2, and then notice it's looking for the mean, which is 138, and it's looking for the standard deviation. Now you have to be careful. This is not the standard deviation that we're given. This is the standard deviation of the sample means. So I have to divide that. So the same way we did with our standard deviation for the z-score calculation, I have to divide that by the square root of 26. And then this function norm.dist asked, is this a cumulative, do we want the cumulative probability? That means, do we want the probability all the way to the left? And yes, we do. So we say true. True will almost always be what you'll want for an introductory statistics class. All right. And now notice, it's about the same as the probability to the left for when we plugged in the z-score 1.13. The reason this is a little different is because it did not do the rounding for the z-score that we did to get 1.13. So this is actually a little more accurate. And then we could do the same thing. Norm.dist for 137.6. Plug in the mean, plug in the standard deviation, and we want it to be cumulative. And subtract those. Now, if we wanted to do this all in one fell swoop, we could put this all in one line. Norm.dist 138.2, 138.9 divided by square root 26, true, minus norm.dist 137.6, 138.9 divided by square root 26, true again. And there's our answer, easily one line.